Hello everyone. In this video we're going to look at something called projectile motion fired horizontally. Before we start, it might be helpful if you had a ruler handy and lots of different colors of markers, because we're going to make a big mess here in our picture. So we're going to be drawing a picture that our notes are going to be kind of like hidden in this picture, so we need to kind of do a really good job with that. So before I talk about projectile motion, I just want to review two things first. So the first thing I want to review is constant velocity, and so I'm going to write that up here at the top. It also would be really helpful if you wrote everything on your notes the exact place that I'm writing it, because I'm kind of planned it out so that I know it's going to fit on this piece of paper. All right, constant velocity. So to review constant velocity, I'm going to pretend that I have a bowling ball, which I'm going to put right here, and I'm going to roll it down a bowling alley. So this is going to be my bowling alley. So that's why I want the ruler, so I can make a nice pretty bowling alley. And I'm going to go like this. And we're going to make some little tick marks on the bowling alley. And we'll do it in meters. So we'll call this one 10 meters and then 20 meters. And I'm going to mark the 20 meters. 20 meters. And this will be 30, this will be 40. This will be 50, this will be 60. So I'm just going to mark like like this, going every other box. I'm going to tilt my paper here just a second. And I'm going to go all the way up, I think, to about 200. 140, 160, 180, and 200. Okay, so quite simply, I now, to review constant velocity, am going to roll my bowling ball with a velocity of 20 meters per second. Honestly, it's a really fast bowling ball, but we're not going to talk about that. All right, so 20 meters per second. So if I rolled my bowling ball, after 1 second, it would go 20 meters. So I'm going to put my bowling ball at the 20. And after 2 seconds, it would be at 40 meters. After 3 seconds, it would be at 60 meters. So I can keep kind of going across like this, because I'm going 20 meters every second. And I won't label all of them, but I do want to put the time on here. So this is where my bowling ball would be at 1 second. This would be 2 seconds. This would be 3 seconds, 4 seconds, 5 seconds, and that's enough that I can write down. All right, so constant velocity means that my bowling ball would be equally spaced. So we know that, and that makes sense now. All right, so before we can do projectile motion, though, we have to review something else. And that is, if something is not moving at a constant velocity, it is accelerating. And maybe the best way to review accelerating is to drop something off a cliff. So we're going to make this my dropping something off a cliff. So I drew another straight line there, and I'm going to put a little cliff in here like this. So we're going to drop something off the cliff, and we are also going to drop a tape measure down here so that we could record the distance that it falls. And I'll do the same thing, like every box stands for 10, but I will label like 20, and then I'll skip a box, then I'll go 40, and I'm just going to go all the way down to the bottom of the page. So 20, 40, that'd be 60, 80, 100, and it looks like I can get to 120, and I have a smidge left there, so my cliff is a little bit taller than 120. All right, so if I was at the top of the cliff and I wanted to drop the bowling ball, we know that the bowling ball is going to accelerate to the ground. So I want to write the word acceleration on the side over here. All right, so let's look at this now. And I'm asking myself a question. How far would the bowling ball fall after 1 second? So I'm going to go down here to the bottom and kind of talk to myself, like how far would the bowling ball fall after 1 second? And since I'm dropping the bowling ball, my equation is going to reduce to d equals 1/2 at squared. D equals 1/2 at squared. We use that equation a lot in the topic of projectile motion. That I like to call it the dropping equation. D equals 1/2 at squared. It will tell me how far something falls after a time, or what time does it take something to fall this distance. So I just said to you, what distance does the bowling ball fall after 1 second? So we'll put a 1 in here, square it. So 9.8 divided by 2 is 4.9. It falls 4.9 meters. So let's go back up here to the bowling ball. And if this is 10, after 1 second, it would be like about right there. And I'm going to put a 1 second next to that. All right, the next one is to put a 2 in here. So 9.8 times 4 divided by 2, it turns out to be 19.6. So after 2 seconds, my bowling ball is right here, 19.6. That's 2 seconds. Then I'm going to go back down here, and I'm going to put a 3 in here. And that's going to turn out to be 44.1, I think, 44.1. I don't trust myself. Hold on. All right, 0.5, that's the 1/2, times 9.8 times 3 squared, 44.1. It is 44.1. Okay, so we'll this is 50, so 44.1, maybe about right there. And we'll call that 3 seconds. All right, let's put a 4 seconds in. That's going to be 1/2 times 9.8 times 4 squared, that's 16. 78.4. So we'll put the bowling ball at 78.4, maybe about right there. And we'll call that 4 seconds. And then let's do 5 seconds. So 1/2 times 9.8 times 5 squared is 25. And that is 122.5. So that's going to be the bottom here. That's 122.5. So my bowling ball hits the bottom in 5 seconds. All right, and that makes sense to me because if the bowling ball was being dropped, it would be accelerating and my dots are getting farther and farther apart. So my point with this is that you understand constant velocity. You understand how the dots are equally spaced. You understand dropping something off a cliff. And when you drop something off a cliff, the initial velocity is 0 and it's going to accelerate down. All right, we are now ready to talk about our new topic today. Our new topic today is projectile motion fired horizontally. So what we're going to do is we are going to go to the top of the cliff, and we're not going to drop the bowling ball. We are going to go bowling off the top of the cliff, meaning that I'm going to kind of run like this is my bowling alley, like I'm running like this, and I'm going to release the bowling ball horizontally. So basically I'm going bowling off the top of the cliff. The issue here and the key point is that the bowling ball doesn't know that there's no bowling alley. So the bowling ball will go bowling off the top of the cliff. And you and I are going to see the effects of what's going to happen. So here goes the bowling ball. It starts here. I let go of it. I go bowling off the cliff. 1 second. Oh, by the way, I'm going bowling off the cliff 20 meters per second. So 1 second later, the bowling ball has gone across the air 20 meters. But at the exact same time, it has fallen 4.9 meters because gravity is acting on it. So 1 second later, the bowling ball is right there if I go bowling off the cliff. After 2 seconds, it has gone over 40 meters, but it has fallen 19.6. So I'm going to intersect these 2 points here. and that's where my bowling ball is. And after 3 seconds, I'm at 60, and it's fallen 44.1. My bowling ball is right there. After 4 seconds, it's over to 80, and it's fallen 78.4. And after 5 seconds, it has gone over 100, but it has fallen 122.5. And so when you go bowling off the cliff, or when you fire something straight out horizontally, you will always get a beautiful parabolic path to the ground. And that's what projectile motion fired horizontally is. I'm going to get this beautiful path. But the point is, we don't have physics equations for this beautiful parabolic path. We instead have to take this path and know that it's made up of things that happened in the constant velocity direction, and it's made up of things that happened in the accelerating direction. So another key takeaway is, if I went to the top of the cliff, and to test this whole thing out, we are going to, let's say, take a gun that shoots a bullet. And this now is the path of the bullet going to the ground. And I drop a bullet straight down. So if I fire a bullet and drop a bullet, they will both hit the ground at the same time. And that's kind of surprising to some people. Some people say, well, because I have to go arc way over here, this is going to take longer. It's like, no, they're going to hit the ground at the same time. Because the only thing that's making it arc out is me firing it with a constant velocity. So it says, what affects how far over the bowling ball lands? The only thing that makes it go over is the velocity in which it was fired. And whether I drop the bullet or fire the bullet, after 1 second, gravity is going to pull the bullet down this far. After 2 seconds, it's going to pull it down this far. After 3 seconds, it's going to pull it down this far. So I will never know what the time it is to parabola down. I'll call that, I'll write it here, time. But I do know that the time to parabola down is going to equal the time to just drop it down. So I'll call this T1 and I'll call this T2. Those times are equal. And that's going to be a big takeaway from this, because we can just use the dropping equations to get the time and know it's the same to arc over here. All right, so what affects how long it takes something to reach the ground? So that would depend on the height of the cliff, because the taller the cliff, the longer it is to hit the ground. The height of the cliff, and I'll say gravity, because gravity is going to pull both of them down the same. All right, I want to make one more other thing on this picture. Is what if I went back to the top of the cliff and I went bowling off the cliff with a velocity of 40 meters per second. 40 meters per second. How would the picture change? Well, after 1 second, the bowling ball will have gone over 40, but it will still have fallen down the same amount. After the second it would have gone over 80, but it would still have fallen down the same amount. Third second, it would go over 120, fall down the same. Then 160, fall down the same. Then it'd be over to 200 and it would fall down the same. Again, it's another beautiful parabolic path coming down to the ground. But what affects how far over the bowling ball lands? The velocity in which it was fired. Because if I make the 20 a 40, the bowling ball is going to end up hitting the ground twice as far over. But the time, I'll call this time 3, is the same is time 1 and time 2. The time to fire it this way, the time to fire it this way, and the time to just drop it is the same. So we're always going to find the time to drop when we need to find these respective times. All right, I'm going to stop this video, but there's actually more things that we need to put on this picture. So please tune in to part 2.